Hello, everyone. Thank you for joining us today for this webinar titled Solving the Problem of EMI Shielding and Fire Protection in Composite Battery Enclosures Using Nonwovens. Brought to you by Composites World and presented by Technical Fiber Products. My name is Jeff Sloan. I am the Editor-in-Chief of Composites World. This presentation will last about 45 minutes, followed by question and answer. If you have a question, you can type it at any time during the webinar under the Q&A tab. This webinar is being recorded and when complete will be made available to you via email from Composites World. A PDF version of this presentation can also be requested directly from Composites World. We have two presenters today. Our first is Mike Campbell, TFP's Technical Sales Representative in the United States, covering the automotive and consumer electronics market spaces. Mike was a panelist at the Battery Show in 2020 discussing the use of composites in the automotive space. He has collaborated with industry professionals to bring TFP's EMI shielding technology to market. He has a degree in engineering. Our second presenter today is Neil Gray, TFP's Business Development Manager. Neil has 25 years of experience in the composites industry in commercial and technology management. He has held a range of R&D and business development and management roles with a focus on FST fume performance systems. He has a degree in chemistry and an MBA. Welcome, Mike and Neil, and it's all yours.
Thank you very much, Jeff, and to the Composites World team. We're excited to be here today. So if there's anything that we want this group to take away from the presentation, it's these three things. Technical Fiber Products supplies rolled goods, not finished parts. Our focus is on custom-made, lightweight nonwovens. They are drop-in solutions in composite parts. And we recognize that a successful composite product requires collaboration, and we want to collaborate with you. So just a brief background on our company. Our parent company, James Cropper, founded Technical Fiber Products in 1986. They make high-quality specialty paper. TFP's nonwoven manufacturing lines are located on the same campus as James Cropper, just north of Manchester, UK. Our engineering, quality, and rest of world sales teams are there as well. In the US, we have a sales team that covers North America and a metal coating operation. Overall, we have about 120 employees with TFP. So our nonwovens are made using a wet laid process similar to the way paper making is made. Rather than utilizing wood pulp and hydrogen bonding, we utilize engineered fibers such as carbon, glass, polyester, aramid, and an organic binder to hold them together. So in the picture on the right, you can see how porous the structure of our typical nonwoven is. You can see the chopped fibers and the organic binder at the intersections. Our materials are used in a variety of applications. Occasionally, they are used on their own. An example of this would be the Whitestone Bridge project in New York. Our intumescent nonwoven was adhered to the composite wind fairings with a self-adhesive backing. Other times, our materials are coated with our customers' proprietary products. They range from adhesive resin systems to coatings used in hydrogen fuel cells. Today, we will focus on our nonwovens used in fiber reinforced plastics, specifically battery enclosures. So this is a very condensed list of applications, and I'll highlight just a few that may also be pertinent to the automotive industry. So glass veils on the surface of a composite part provide a layer for resin to evenly spread across the peaks and valley of a woven product. Our customers use this when they see pitting, air bubbles, or other surface defects. Aramid is used on the surface of composite parts as well, as it is very tough and protects from oversanding during production and from abrasion while the part is in use. An example of this could be the underside of a car, cargo containers, or pallets. The rest of the presentation will focus on EMI shielding and fire protection within composite battery enclosures. All right, Neil, over to you.
Thanks, Mike. Good afternoon or evening, everyone from the UK. Thanks for tuning in, and thanks to Composites World for the opportunity to present this webinar. I'm Neil Gray, the Business Development Manager at TFP, and I'll be looking at how Technofire intumescent veils can help in meeting the thermal and fire requirements for composite battery enclosures. I'm sure we're all aware that the electric vehicle market is booming. In 2019, 2.5% of all cars were EV. By 2029, this is forecast to grow to more than 25%. And the market is running at a very attractive 20 to 30% CAGR. More cars means more EV batteries, and as batteries become larger to give better range and more power, weight becomes more of an issue, which is where composites can offer a significant advantage. However, a move from metal battery enclosures to composite ones can provide some challenges in terms of EMI shielding and fire and thermal protection. And in this webinar, we'll look at how these two areas of concern can be addressed using TFP's non-woven functionalized veils. So let's start with an introduction to the Technofire technology and product range. Technofire is a range of lightweight, intumescent fire protection materials based on high-performance fibers and specialty grades of graphite. There are Technofire products with different activation temperatures of either 190 degrees C, 374 degrees Fahrenheit, or 220 degrees C, 428 degrees Fahrenheit. And once the Technofire veil reaches its specific activation temperature, the graphite intumesces or expands in the Z direction, forming a stable, insulating carboniferous char layer, which insulates and protects the backing laminate. The Technofire range is well established and has been around for over 30 years. Numerous grades of Technofire are available, some containing other FST or fire, smoke and toxic fume performance additives such as ATH aluminium trihydrate to further improve fire and smoke performance. The material is available in flexible and rigid forms and in a wide range of sizes, from rolls and sheets to narrow coils, and the organic content is generally less than 10%, so the materials are inherently non-flammable. Technofire was originally developed for gap-filling applications, such as fire doors, but it's been used in composites successfully for over 20 years, including the Whitestone Bridge in America, which Mike mentioned, where over 20,000 square meters of Technofire-enabled composite panels were used, making it the biggest composite infrastructure project at that time. Composite-specific grades are available, and these have been specifically designed for use in a wide range of composite manufacturing processes, including RTM, vacuum infusion, pultrusion, filament winding, compression molding, centrifugal casting, pre-pregging, with a wide range of resin systems, including epoxy, polyurethane, vinyl ester, unsaturated polyester, and phenolics. And one of the key attributes that makes Technofire really attractive for composite battery applications is that they are a simple drop-in solution with generally no changes needed to the resin, the reinforcing or manufacturing process. And they can really be thought of or visualized as functionalized surface veils that afford a high level of fire protection. This video shows the intumescent effect of Technofire as it expands to form the stable carboniferous char which protects and insulates the backing laminate. This particular grade is a development grade, which is activated remotely by passing a current through the veil to achieve resistive heating, which allows it to be activated in advance of a fire. The technology used to make it conductive also affords EMI shielding, so there is the potential to have both fire and thermal protection and EMI management in one simple drop-in product. We are always looking for new developments to satisfy growing market needs, and the current commercial grades activate at either 190 or 220 degrees centigrade as highlighted, but we are working on grades with 250 degrees C, 482 degrees Fahrenheit, and 280 degrees C, 536 degrees Fahrenheit activation temperatures to open up more thermoplastic applications, such as polypropylene and polyethylene, which Technofire bonds well to. As an introduction to the potential improvements in fire performance by incorporating Technofire into composites, I'd like to briefly present two recent composites projects before we move on to battery applications. And the first of these is the Valmont utility pole case study. I'm sure everyone is aware from the news of the increased frequency of wildfires around the world. Classical wooden power or utility poles are easily destroyed during a wildfire, leading to power outages and significant expense in re-establishing the network. Valmont in America have developed a composite utility pole which passes the USA Utility Company Consortium fire tests, which mimic exposure to a wildfire with temperatures of 2,100 degrees Fahrenheit. The poles are made using filament winding or centrifugal casting, incorporating an infusible grade of Technofire during construction. And the Technofire intumescent veil activates and expands during a fire to protect and insulate the backing laminate and ensure the structural integrity of the pole is maintained. The poles had to pass a number of fire tests, including the extreme wildfire test, where the pole is enclosed in a steel culvert and a significant fire is established, reaching, as I mentioned, 2,100 degrees Fahrenheit, as seen in the photos. And I think these really highlight the severity of the test and how challenging it is for composites to successfully pass this test. And you can just see in the middle photo, there's a wire attached to the top of the pole. The pole is actually under flexural load during the test to assess retention of mechanical properties during and after the fire. As well as the extreme wildfire test, the poles also had to pass UL 94 V0, ASTM E84 Class 1, and the D1036 pole bending test, so a wide range of demanding tests assessing fire retardancy, fire resistance, and retention of mechanical properties. And the insulating carboniferous char is clearly visible in the photo on the right of the slide. And I'd like to thank Eric at Valmont for working with TFP to make this project a success and for letting us present the results today. The second project I'd like to briefly touch on is a recent 3-year study in China assessing the impact of Technofire in composites to the European rail standard EN 45545. This was a 3-stage project. Stage 1 was manufacture of monolithic, non-fire smoke and toxic fume rated carbon fiber and epoxy prepreg panels with and without Technofire, and then testing to the rail standard. Stage 2 was manufacture of sandwich panels from the same prepreg, again with and without Technofire, and testing to the standard. And in stage 3, a window frame demonstrator part was made. And I'd like to briefly highlight some key results from stages 1 and 2. So these are the stage 1 results comparing performance of the non-FST, the non-fire smoke and toxic fume performance rated monolithic prepreg laminate as the control to the same laminate incorporating a 0.5 millimeter layer of Technofire E20 EMI. And I just want to focus on the MARE, the maximum allowable heat release rate, highlighted there in blue on the first line of the table. So why is heat release rate important? Heat release rate is a critical measure of fire performance of a composite, as it assesses how much energy is released by the laminate, which feeds the fire, and how quickly this energy is released. So a low number is good, meaning a relatively slow growing fire, and conversely, a high number is bad. For the control non-FST rated laminate, the MARE result was 177, shown above in red, which is pretty high. However, by simply incorporating the 0.5 millimeter layer of Technofire onto the surface before compression molding, this result has been reduced to 63. An improvement or reduction in heat release of 65%, or 2/3, by simply dropping in this thin layer of Technofire. In the second part of the project, the same procedure was repeated, but this time on a sandwich panel using the same non-FST rated prepreg. In this case, the control panel gave a MARE, the maximum allowable heat release rate, result of 98. So better than the stage 1 monolithic panel, but still a high heat release rate. And again, by simply incorporating a 0.5 millimeter layer of Technofire E20MI, the maximum heat release drops to 51, an improvement of 48%, or pretty much by half. The smoke results, DS4 and VOF4, which are both smoke measurements, also show significant improvements, from 270 down to 180 for DS4 and 700 down to 430 for VOF4. So whilst not directly battery related, hopefully these two composite projects give an idea of the potential impact in terms of fire protection of introducing Technofire into a composite battery enclosure. So let's get back to EV batteries. That's what we're really here to talk about, and focus on the test standards for the growing composite battery enclosure market. The first thing to say is that this whole area is developing in real time as the market grows, with standards and testing regimes being recently updated. Previously, the key standard was the GBT 31467, also known as the Chinese bonfire test, which was originally derived from a fuel tank standard and was a really stringent standard to pass, with temperatures of 600 degrees centigrade for up to 2 minutes and a peak of 800 degrees C. This has now been updated to a suite of 3 standards, with GBT 38031 really being the lead standard for passenger cars. And this standard is even more stringent, with a 5-minute egress alarm and a higher test temperatures of up to 1,000 degrees centigrade. I'd now like to move on to present some results from an ongoing composites battery enclosure project we've been working on with our partner Ford Engineering in Germany, and I'd like to thank Dennis Schmidt for allowing us to present the data in this webinar. So as a brief introduction to Ford Engineering, their focus is on being a design and engineering partner for automotive lightweight solutions by bringing together structural design, manufacturing process, and advanced materials with a focus on the early concept phase. This slide gives a few examples of lightweight and demonstrator battery projects they've successfully worked on recently using multi-material design for end customers such as NIO and Vistaro. So let's get into the results of the project. The first stage of the project involved 36 experiments. 3 different grades of Technofire intumescent veil were incorporated into composite laminates before manufacture. The post-cured laminates were then exposed to 800 degrees centigrade, 470 degrees Fahrenheit, 600 degrees centigrade, 1100 degrees Fahrenheit, or 400 degrees centigrade, 750 degrees Fahrenheit, via direct gas flame exposure for up to 15 minutes. And the back face temperature measured. So these experiments are really assessing the thermal insulation abilities of the Technifier veils to protect the backing laminate. And any damage or degradation of the laminate was also assessed. The test procedure can be seen in the diagram with the Technifier enabled laminate supported on a heat shield and 2 pillars. The gas flame directly impinges the front or top face, with the exposed face temperature being measured by thermocouple 1, and the back face temperature is measured by thermocouple 2. And as a brief summary, the 800 degrees C or 1470 degrees Fahrenheit experiments exhibited a maximum back face temperature of 150 to 250 degrees C or 300 to 480 degrees Fahrenheit. So a temperature reduction of 550 to 650 degrees centigrade or 1000 to 1200 degrees Fahrenheit through the insulating action of the Technifier intumescent layer. So let's look at the actual results on the graph. So apologies, this graph is a little bit busy, but summarizes the thermal results with Technifier T666301, which is a 70 gram per square meter Technifier grade at 0.37 millimeters thickness. So really thin, lightweight fire protection material. Time is on the x-axis and temperature is on the y-axis. And you can see from the lines towards the top of the graph, the front face of the laminate pretty quickly reaches 800 degrees centigrade or 1470 degrees Fahrenheit, and the experiments are then stopped at either 5, 15 or 20 minutes. And if you look now at the graph, the lines towards the bottom of the graph, the back face temperature is generally 550 to 650 degrees C or 1000 to 1200 degrees Fahrenheit lower than the front face temperature, showing the insulating effect of the Technifier, affording a high level of thermal protection to the backing laminate, which would be critical in the event of a battery thermal runaway. These pictures show the worst case damage in the T666301 laminate from the 800 degrees centigrade experiments. On the right, you can see the exposed face of the laminate, and due to the high temperature and the ablative nature or effect of the gas flame, some of the resin has been burnt off. However, the photo on the left shows the back face of the laminate, which has experienced significantly lower temperatures due to the insulating effect of the Technifier. And you can see there's no distortion, delamination, or degradation of the laminate structure, with just some minor discoloration. This highlights, in a thermal runaway event, how the intumescent mode of action of Technifier can protect the composite battery enclosure structure. Again, I'd like to thank Dennis at Ford Engineering for the agreement to present this data, and their contact details are given on the slide. And I'll pass back to Mike to pick up the EMI shielding discussion. Over to you, Mike.
All right, thanks, Neil. So to start with the EMI shielding in battery enclosures, we need to start with the raw materials. In Schenectady, New York, we coat fibers with metal. These fibers get sent to our UK manufacturing plant, chopped, and used in our metal coated veils. Copper and nickel are the two primary metals we use, but we can also coat with silver, gold, tin, and specialty alloys. So in the bottom left picture, you can see a cross section of carbon tow that we have coated. It provides a great visualization of how evenly coated each individual carbon filament is. So this here is a conductivity spectrum showing various materials. On the left side, you have your very conductive materials like copper bus bars, and on the right, you have plastics, dielectric materials. We like to say that we play in this region. So on the left side would be our copper nickel coated carbon veils, and on the right would be our glass veils. Anything in between we can make using a combination of the fibers. So we could combine carbon and glass to change up the conductivity. So the application we're talking about today is EMI shielding. However, I should also point out a few others. Our conductive veils are used for resistive heating. So similar to the way a toaster works, if you run current through our metal coated veils, they will heat up. An example of that was in a video that Neil showed a few slides back, where the Technofire expanded. That was because there was heat caused by the current running through the material. Another application is inductive welding, thermal conductivity, or electrical conductivity. So going back to the very first slide I showed, I mentioned how our materials are a drop-in solution. The veils can be added to most manufacturing techniques and have been successful in both thermoset and thermoplastic resin systems. So the data I'll show you today will be at a material level, not a part level or systems level. There are multiple ways to test for EMI shielding, but in summary, you take your material and attempt to send a signal from one side to the other. Then you run a calculation to determine the loss, or otherwise known as attenuation. So on the right side of the slide here, you'll see a calculation from ASTM D4935. I want to point out the logarithmic function here, as this will help you understand the units and scale that you'll see in the following slides. So that calculation will yield a shielding effectiveness in units of decibels. So an example here is if you get 10 decibel of shielding effectiveness, that would be a signal attenuation of 90%, or in other words, 10% pass through. If you get 50 decibels, you're at 99.999% signal attenuation, or only 1/10,000th of a percent pass through. So for some context, we have heard target shielding effectiveness numbers in the 30 to 60 decibel range in battery enclosure applications. There is a correct number. It comes down to the OEM and the design requirements. So here's some ASTM D4935 testing that we've had done on our nonwovens. Here you'll see three materials: carbon, nickel, and copper nickel coated carbon veils. So the carbon veils are least expensive, but also the least effective. Those are the squares on the bottom of the graph. In the middle, the circles is the nickel coated carbon veil. This is our most cost effective as far as shielding effectiveness goes. So I like to point out the red, the 34 grams per square meter, the red circles here in the middle. You'll see here at the lower frequencies around 30 megahertz, you get about 50 dB. And at 1500 megahertz or 1.5 gigahertz, you're around 55 dB. This is usually where I like to start customers with shielding with EMI shielding applications in battery enclosures. So this slide here points to how the veils used in composites are similar to how the veil is measured on its own. So in the middle column, the veil only was tested at 10 gigahertz. And you can see that the carbon at 10 GSM yielded about 27 dB. And within a composite, which was a glass epoxy prepreg, was 25 dB. So really no significant change here. I will also like to point out how the carbon is, you can see how it's a little less effective than the nickel coated carbon, and that's less effective than the copper and nickel coated carbon. So this was in the same experiment as the previous slide. There was a glass and epoxy prepregs, but here we attempted to stack our veils to see if that would add to the EMI shielding effectiveness. So this is a little bit busy, but let's look at just the 17 gram per square meter nickel coated carbon. So with one layer, it yielded 40 decibels of shielding effectiveness. If you had two layers of the 17 GSM, or another way of saying that would be 34 grams per square meter in total, you got 60 dB. You can follow that graph up and you get 80 dB at 3 layers. For some reason, it dropped at 4 layers. All right, now for a case study. TRB Lightweight Structures is a customer of ours that specializes in lightweight products for the transportation industry. Like us, their headquarters is in the UK, while their high volume manufacturing is in the US. TRB has a unique pre-preg line that can go from raw materials to part all in one process utilizing robotic manufacturing. So this is an example of a commercial product in the automotive industry utilizing our conductive veils in the automotive industry for EMI shielding. I really want to thank Teresa and Ben at TRB for allowing us to share these slides. If anyone has any questions for them, please reach out. Ben's contact info is on the bottom of the slide there. All right, now over to Neil to wrap it up.
Thanks, Mike. So to summarize, the EV battery market is growing rapidly, and composites are seen as a key lightweight enabler of that growth, but can present challenges in terms of EMI shielding and fire and thermal protection. TFP's functionalized non-woven veils are ideal for use in composites design and manufacturing, and can provide solutions for effective EMI shielding and fire and thermal protection with a simple drop-in material approach. Thank you again for listening, and to Composites World for the opportunity to present, and we're happy to take questions.